Okay, this is part 3 in a series devoted to the third time's a charm principle. Okay, so what I thought we would do is begin with an effect that you can do right away. Okay, so I've shuffled the cards a few times there, and so what we're going to do is we're going to show a most remarkable phenomenon. We're going to have both of us state our favorite card in the deck, and then I'm going to use your favorite card to actually locate my favorite card. Wow. Okay, so we only need a handful of cards for this. So what I thought we would do is go ahead and just spell favorite using the Klondike shuffle. So this is where you take the top and bottom off as one. So F, A, V, O, R, I, T, E. Okay, so that gives us a good random selection of cards to work with. Okay, now to be fair, I'm going to go ahead and tell you what my favorite card is so that you don't think I've changed my answer based on your favorite card. Okay, so my favorite card is the 5 of Hearts. Okay, so what is your favorite card? Now, as a note to you as a performer, the spectator could state the 5 of Hearts or any other card in the deck, and you're going to be just fine. So let's say they say the Queen of Diamonds. Okay, the Queen of Diamonds is the spectator's favorite card. Well, you would just say, well, very good. I'm going to sandwich the 5 of Hearts between your favorite card, which you've told me is the Queen of Diamonds. So let's go ahead and just spell out Queen of Diamonds. So Queenofdiamonds. Okay, Queen of Diamonds. Now my favorite card, as I mentioned, is the 5 of Hearts. Fiveofhearts. Okay, and so to properly sandwich the 5 of Hearts between the Queen of Diamonds, we'll spell the Queen of Diamonds a second time. Queenofdiamonds. Okay, well, in what sense has this process located my favorite card, the 5 of Hearts? Well, let's go ahead and just take a look at what card has risen to the top after this quite convoluted procedure. Is it the 5 of Hearts? It is indeed. So if you follow these steps as shown here, this will work for you every time. Now, what we're going to look at today is why that's the case, and also give you many more powerful ideas for taking advantage of this most remarkable principle. Okay, so maybe towards the end we'll talk about this particular effect. I'm hoping that after we go through our explanation, you'll be able to see how it was done and deduce all of the important procedural steps that make it work. Okay, so let's go ahead and take a look at our write-up. This is from part 2, if you recall. In fact, let's go ahead and just kind of bring this over for a second. So a quick reminder. So in contrast to routine 1, maybe I'll just slide this down a little bit. In contrast to routine 1, where we coded, we spelled out and transferred a certain number of cards. In fact, it was half of the packet size. So remember, the setup for this one is you Klondike shuffle a number of pairs to the table. Let's say we have n pairs. That will give us 2n cards total. So in routine 1, we coded n cards, so half the number of cards in the packet 3 times. Okay? Now we didn't do that here. Remember, I spelled out your favorite card, which has a different number of letters than my favorite card. Okay, so this is genuinely different and new today. So let's go ahead and kind of explain that. Okay, and let me point out, in some ways, the write-up is perhaps more for the mathematically experienced viewer than maybe the typical viewer. So I want to explain this information that we just looked at here, where we have the first and third, so first coating's right here, third coating's here. If you notice, we're working with the same number of cards. And then the middle coating has a different and larger number of cards. Okay, so how do we actually read this? Well, suppose we need only 12 cards for whatever effect. So if we're going to use the Klondike Shuffle in the way that we've been using it, Klondike shuffling 6 pairs to the table will give us 12 cards. Okay? So what we're free to do is we don't have to coat the same number of cards 3 times, as we did in part 2 of this series. You can actually coat fewer cards at first, but then you have to be careful to coat more cards for the middle coating. Okay, so that's what I'm going to show you here. So let's suppose for these 12 cards, we coat 5 cards for the first and third coatings, which is 1 card less than n equals 6. That means then we need to coat at least 1 more card than n equals 6 for the second coating. In other words, for the second coating, we need to coat either 7, 8, 9, 10, 11, or 12 cards. Okay, so here is, at the bottom here is our first coating. In fact, it will be our first and third coating. It has 5 cards in it. Well, we need to coat a number of cards that's at least 1 larger than n equals 6, for the simple reason that 5 is 1 less than n equals 6. So any of these values could be used. So let's go ahead and demonstrate that right now. We Klondike shuffle 6 pairs to the table. Okay, so that's what we're going to do. Now, as I noted already, you need to be aware of the identity of the bottom card. Okay, so that's something you could peek or glimpse at the beginning. You could even give the spectator the cards. They can mix them freely, and then you can just kind of nonchalantly straighten them up on the table, square them up. And from my angle, I can see that that's the 6 of hearts. You can't quite see it, but I'm further over this direction, right? So even angled like that, I can see the 6 of hearts perfectly fine. So you just square it on the table and have your eyes kind of look above it, but you can still see the 6 of hearts down there. Okay, so that's going to be, quote, my favorite card. Okay, so that's my favorite card. And now we're going to Klondike pairs of cards to the table, namely 6 of them. Okay, so this would be 1 pair, 2, 3, 4, 5, 6. Okay, so we have 6 pairs of cards. Well, of course, that gives us 12 total. Okay, now the claim is, so going back to our write-up over here, maybe I'll even kind of put it like this so that we can see everything a little bit better. Okay, so for our write-up on the left, I'm claiming that if you, quote, coat 5 cards for the first and third coatings, and then any of these number of cards down here, 7, 8, 9, 10, 11, or 12 for the second coating, that original bottom card will rise to the top. Okay, so if you think about that, that is most remarkable. So let's go ahead and coat. We'll just coat 5 cards. We won't spell like a card value name or something. Okay, so 1, 2, 3, 4, 5. We just coded 5 cards. Okay, now you're free to choose any of these. So maybe you want to go with 8, let's say. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. That's the second coding. Okay, and now if we coat 5 cards again, 1, 2, 3, 4, 5, it is guaranteed that the original bottom card of the packet will rise to the top. Okay, and that's independent of our choice down here. We could have chosen 7, 8, 9, 10, 11, 12 for the second coding, as long as we choose 5 for the first and third codings. Okay, so if you think about it, in fact, maybe we'll just give one more example here in a minute, but if you think about it, what would be a good name for what is going on here? Because in some sense, I'm sandwiching the 8 between 2 codings of 5 cards, because we coded 5, then 8, then 5. So what do you think would be a good name for this principle? Okay, so we'll come back to that in a second. Why don't we just do this one more time with one of the other values? It really is hard to believe. So let's say, just to keep things from getting too confusing and making you remember too many different cards, we'll stick with our 6 of hearts here. Okay, and we'll keep our coding of 5 for the first and third codings, but then we'll change the second coding. So we'll go ahead and code 5. 1, 2, 3, 4, 5. Okay, now you're free to choose any of these. Maybe we'll choose 10 this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we're going to sandwich that between our coding of 5 cards. So we'll code 5 cards one more time. 1, 2, 3, 4, 5. It is guaranteed to bring the original bottom card to the top. And it has again. Okay. Most remarkable property here. Now you may want to notice something interesting about the values here. Okay, so we dealt out 6 pairs, which gave us a total of 12 cards. So 12 cards. And then we said if you coat 5 cards for the first and third coding, so over here, that's like the first coding, third coding, we're free to choose any number of cards to code here, provided it's from our list down here. Well, is there anything interesting that you notice about these particular values? So what we're saying is we could code 7 or 8 or 9 or 10 or 11 or 12. Is there anything interesting that you see as a relationship between the value 5 on either end and the values listed for the second coding? Okay? And then their relationship to the total number of cards in the packet. Is there anything that you see that's interesting? Is there any, quote, inequality we could write down that's true for all of the values that we've listed here? Well, there actually is. Because if you think about it, the first coding, which is the same as the third coding as far as the number of cards, right? That's 5. Okay? Now for the middle coding, the second coding, it can be any of these values. Well, relate these to the packet size if these 5 cards are added to any of these values here. Are we not guaranteed that a card from a number from this list is going to be bigger than or equal to 12, which is the packet size. So any one of these values, when added to 5, gives you something that is equal to or larger than 12. Well, that ends up being the requirement that makes this work. Okay? So as long as the number you use for the first and third coding, you just take the single value, here it's 5, and the number of cards coded for the second coding, if those two numbers combine give you a number that is 12 or larger, this entire routine that I've just shown you will always work. Okay? So let's go ahead and maybe just show one more quick example of this using different values now. Okay, so suppose we want n to be 7. So we're going to, quote, Klondike shuffle 7 pairs to the table. Okay? So we start with a known card at the bottom. You can actually shuffle the cards as long as you let the left-hand card fall, bottom card fall first. Okay, so it's still at the bottom. We'll stick with our 6 of hearts. Okay, so just left falls first. Okay, and now if we Klondike 7 pairs to the table, so 1, 2, 3, 4, 5, 6, 7, that will give us, of course, a total of 14 cards. Okay, and now suppose we want to coat 4 cards for the first and third coatings. What would be the range of values for the second coating that will allow our bottom card to rise to the top? Okay, well, think about it. Just think about it here. So we're going to, technically for the first and third coating, we're going to coat 4 cards. So we have 4 cards. So 4 plus what is going to be larger than or equal to the packet size of 14. Well, as we can see here in this inequality, what can go in for the, quote, question mark, it's going to have to be a number larger than or equal to 10. Okay, so this can be 10, 11, 12, 13, or 14. Now we can't go over 14 because we only have 14 cards, right? So that's what I've listed down here in my little graphic. That if the first and third coatings are 4 cards, then you're free to choose any of these number of cards to be coated for the second coating. And that bottom card will rise to the top. So let's just demonstrate that quickly here. So if we coat 4 cards, 1, 2, 3, 4, and then you're free to choose any of these. Maybe we'll choose 13, let's say. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then we coat 4 one more time. 1, 2, 3, 4. It is guaranteed to bring the original bottom card to the top. There it is, okay? And if that's my stated favorite card, this process has brought my favorite card to the top, okay? So let's talk about what would be a good name for this principle that would help us remember what is going on with the principle. So let me just point out what the original name for this principle is, and an alternate name that I think will help you remember what's going on a little bit better, okay? So the original name given to this principle is, and it's called an off-centered coding, okay? An off-centered coding. Now, that's a very descriptive, though fairly technical name for what's going on. So that's a very, very good name to give it if you're going to be precise in what you're describing. Because if you think about it, this off-centered, what it means is if This is the number of pairs of cards dealt to the table. So you have n pairs for a total of 2n cards. If you coat a certain number below that, that's what we're indicating here, below that, let's say m units below n, then you need to coat, so that if this is for the first and third coatings, you need to coat that amount, but on the other side, kind of equal distant from the center. That's what it's called off-centered overcoating. But not only that, you can also coat beyond that number up to the total packet size. Okay? And so that was what we were seeing with the previous write-ups, if you think about it, right? Because I indicated, so this one here, 4, is 3 units below n equals 7. It's 3 units below, 1, 2, 3. Well, what that means then is you're going to have to coat at least, so 1, 2, 3, above n equals 7 for the second coating. And so if we coat at least 10 or more, this phenomenon will work for us, okay? So the original name is off-centered coating. Now, what I've decided to call it is the sandwich principle. If you can't quite see why I would use that word, let's go ahead and just kind of quickly explain it then, okay? And I think it'll help you stay on track, actually, if you think about it as the sandwich principle, because that's really what we're doing. Okay, so why do I call it the sandwich principle? It's because the word, whatever name we're counting out or spelling out, I just call it word, it could be a phrase even, because the, quote, word to be spelled out for the second coating is sandwiched between the word for the first and third coatings, okay? So here's a little diagram to kind of make that clear. So we have a word chosen, word 1. Now this same number of cards for this will be used for the first coating and over here for the third. So that's why I have a word 1 there and a word 1 here. These need to be the same number on the outer ends. Well, it's like this, whatever this word is, it's sandwiching between them the word for the second coating, okay? So just visually, and in terms of the procedure itself, there really is a sandwiching that's going on, okay? So that's why I gave it the name that I have. And I do want to tell you that what I'm showing you now technically covers not only what we've been talking about with this routine 2, but also it covers and explains routine 3. So it really is the case, if you want to come back to this write-up later, that what I'm going to show you now actually covers both of these cases here. Okay, so we'll let T, capital T, represent the total packet size. Now, up till this point in the presentation, it's been 2 capital N, because we were Klondike shuffling N pairs to the table. Well, we don't need to restrict ourselves to an even number for the packet size. It can be actually any packet size. Let little n represent the number of letters in the word to be used for the first and third coatings. And of course, this little n needs to be less than or equal to capital T, our total packet size. We don't want to coat more cards than we have, right? If we do that, that's called a hypercoating, which is a completely different topic. Amazing topic, but a different topic. And then if we let little m represent the number of letters in the word to be coated for the second coating, where once again, little m needs to be less than or equal to the total packet size, the bottom card of the packet will rise to the top, provided that the sum of n and m is at least as big as the packet size T. Okay, so it can be identically equal to t or any value larger than t. Okay, so keep that in mind. And you can check all of that against what we've done so far. We've satisfied all of those conditions in the performance and the examples I've shown you in this video. The difficulty for most people comes from the fact that we have what's called an inequality. So we have a greater than or equal to sign here. But there are three variables. Okay, so we have an n, m, and t. Okay, so that's quite a bit to keep track of. Okay, so because of this requirement here, there are many ways to design routines based on the sandwich principle, this off-centered coding principle. Okay, so for example, we can choose the packet size t first. So maybe we'll say we want 16 cards to work with, let's say. And once you've chosen the packet size, that puts a restriction on what the values n and m can be for all of this to work. Okay? That would be one way to proceed. Another way to proceed would be if we happen to have two words in mind with n letters and m letters. Okay, so let's go ahead and give you an example. Suppose you want to use the phrase, run, Scott, run. Well, if you notice what's going on here, this is a perfectly legitimate triple to use. So if we spell run, followed by Scott, followed by run, it will bring the original bottom card to the top. Now, it's only going to do that if the total packet size is within a certain range. Okay, so that's what we're going to show you now. Okay, so notice here, so the first and third codings involve 3 letters. So 3 cards will be dealt down. The middle coding involves 5 letters. Okay, so n is 3, m is 5. Well, think back to our inequalities. Now, first off, we need our total packet size to be bigger than or equal to both of these. So the packet size will have to at least be 3, but more than that, it needs to be at least 5. Okay, so packet size t needs to be greater than or equal to 3 and greater than or equal to 5. Well, that means it needs to be greater than or equal to 5. Okay, so 5 is kind of a lower bound for the packet size. Now, what's the biggest we can go with the packet size? Okay, because we can't choose too big of a packet size because the sandwich principle will not apply. Well, how big can we choose? Well, remember, we need t to be less than or equal to the sum of these two values, n and m. Well, n plus m is equal to 8. And so that would place our total packet size that's going to work for us somewhere between 5 and 8. So if you choose somewhere between 5 and 8 cards, and then go through this little routine here, it's guaranteed to bring the bottom card to the top. Okay, so let's go ahead and kind of demonstrate that. Okay, so what we need here is we need the 4 aces in some order, it doesn't actually matter, at the top of the deck. So that's kind of where you begin with the routine. Now you can go ahead and riffle shuffle this if you would like. You just need to preserve the top 4 cards at the top, 4 or more. Okay, so it's not too difficult to preserve 4. Much more than that, it's kind of hard actually. Okay, so just to show you, we still have the 4 aces on the top. Okay, but the spectator probably believes the cards are mixed, where no one knows where anything is. Okay, so what we're going to do is we're now going to spell out 4 aces. Well, why is that a good choice? Let's go back to our write-up here. The total packet size can be anything between 5 cards and 8. Okay. Well, the phrase 4 aces has 8 letters in it, so it's going to work just fine. Okay. So we'll go ahead and spell out 4 aces. F-O-U-R-A-C-E-S. The 4 aces. Whoa. Okay. And then you can tell the spectator that you've always been mystified by the phrase, run, Scott, run. I don't know if that's a phrase you've heard before, but it's kind of a classic one. And because of the repetition of the word run, it's perfect for this sandwich principle. Okay, so tell them, I've always been amazed by this phrase. It just seems to accomplish surprising things. Okay, so now we're going to perform this, quote, triple coding, this sandwiching of Scott between the word run. Okay. Oh, I guess I should point out, remember we had the 4 aces at the top of the deck. We retained them there through a couple of riffle shuffles, and then we spelled out 4 aces, which is 8 cards. Well, that moves the 4 aces to the bottom, right? Okay, so the 4 aces are now on the bottom of the packet of 8, right? So I think you probably realize that. Okay, so let's go ahead and just check out this phrase, run, Scott, run, and see what it leads to. So run, R-U-N, drop the rest on top, Scott, S-C-O-T-T, run, Scott, run, R-U-N. Okay, so is there evidence that this kind of phrase, run, Scott, run, is kind of amazing in some way? Well, let's see what cards have risen to the top because of this. Oh, that's nice. Ace of spades. Oh, you've got to be kidding me. No way. The 4 aces, which we counted out at the beginning. 4 aces. We counted out 8 cards. They've risen to the top of this riffle shuffle deck after we've spelled out run, Scott, run. Wow, there really is something to that phrase. Now, what a person could have done too is you could have, below the 4 aces, you could have put the Queen of Hearts. I've done that before. As kind of a finale, you could have the Queen of Hearts appear here, which is one of the most popular cards in the deck. Okay, but I haven't done that here. Okay, but you could. It's not too hard to do. Okay, so that is an example of choosing words first, kind of a triple, where the first and last ones are really the same words, or same number of letters at least, and then the middle one could be a different number of letters. And then as long as you choose your packet size judiciously, as we've talked about already, this sandwich principle will apply and allow you to accomplish amazing things. Okay, so I want to also point out that what we did with the 4 aces goes beyond kind of what we've done so far in this series. So I want you to see or clearly understand that not only does the bottom card rise to the top, after the sandwich principle has been applied, the bottom M cards, which is the number of cards coded for the second coding, the bottom M cards of the packet that you're beginning with to now perform your triple coding on, those M cards move to the top, but in reverse order. Okay, this is really powerful here. Okay, so what we're going to do here is I'm going to just get out, I guess we can do it with 8 like we did before, but okay, so I'll get out 8, the first 8 hearts, okay? And then what we're going to show is, we're going to show what happens to the ordering of that packet, okay, after we go through this procedure, okay? So I think that's all of them. Oh, one more. Okay, so let's go ahead and we'll put these in order so that we can demonstrate this statement here, okay? So we want ace first, and then 2, and then 3, 4, 5, 6, 7, 8. Okay, so we have a little packet in sort of numerical order, right? A value. Okay, so what I'm claiming then is, remember the M, we coat N, little n cards, then M, then N. Okay, so this M here is referring to the number of letters in the second coding, the middle coding, right? So let's go ahead and just apply it to the run, Scott, run. Okay, so we'll apply it to that. So run, Scott, run, like we were just doing. Well, the middle coding here is Scott, which has 5 letters. So let's see what happens when we go through this procedure. So now remember, what's on bottom, though? We need to make that clear. So what's on bottom is 8, 7, 6, 5 in that order, right? If you're reading it from the bottom, it's 8 down to ace on top, okay? So R-U-N, okay, run, Scott, S-C-O-T-T, and then run one more time, R-U-N, okay? Now the claim is that the original 5 cards, because Scott has 5 letters in its name, the original 5 cards of this packet have risen to the top, but in reverse order. What does that mean? That means that the top card here will be an 8, and now it's going to be a 7, 6, 5, 4, okay? So that is the bottom 5 cards in reverse order. Now the other ones will not be in order, in that same order. They'll be actually in their original order from the top of the deck, top of the packet. So we have 8, 7, 6, 5, 4. Okay, that was from Scott. And then the other cards in this particular case here will just be ace, 2, 3, but not in reverse order. Okay? So that's a really powerful principle that you can preserve not only the bottom card, the bottommost card, but you can preserve the bottom M cards as long as you realize that they will now be in the reverse order to what they were in the starting packet. Okay? So that's great. So that's one more principle one more consequence of the sandwich principle. Okay, and so here I just have a statement I leave as an exercise for the viewer to figure out how the opening card effect was done. Okay? Well, I think you probably already know how it was done, right? Because if you go back to the beginning, we had 8 pairs, so 16 cards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 cards. Okay. In fact, maybe we should kind of go through the calculations for this. Okay, so think back to what we did. It was using your favorite card and my favorite card to locate my favorite card, which is like amazing. Okay, so I started with 16 cards. Okay, so why don't we write this down? So T equals 16. Okay, and then we worked with, I think I sandwiched your favorite card between mine. Do you remember that? So the blue, the N is my favorite card, and the red M is yours. Okay. Well, why is this always going to work for us? Well, think about it. Let's say for N. Now, you may not be aware of this, but what is the shortest card value name? How many letters does it have? Well, the shortest would be something like Ace of Clubs. So that's ACEOFCLUBS. Okay? So N is guaranteed to be, it'll have to be at least 10 letters. Now, what's the longest of the card value names? Well, it ends up being 15. So like Queen of Diamonds. QUEENOFDIAMONDS. That's 15 letters. Okay? So, and this will be true for the spectator's chosen favorite card, right? It will, no matter what they name, it's going to have somewhere between 10 and 15 letters in its name. Okay? Well, why is 16 going to work for us as a total packet size? Okay, so what needs to be true here? Okay? Well, first off, we need, remember, let me get the black one here, I guess. We need n. It needs to be smaller than or equal to t. We need m to be smaller than or equal to t. And then 3, we need t to be smaller than or equal to n plus m. Okay, so are all 3 of these inequalities satisfied? Well, this one is here, right? Because the largest n can be is 15, right? So the largest n can be is 15, which is less than, or equal to, but less than 16, okay? So that inequality is satisfied, right? In fact, maybe what I should show here is technically ahead of time, we don't know what these are, but we do have a range of values that they can be. That's the key. So they have to be somewhere in that range. And the same thing with M. The spectator's chosen favorite card will have somewhere between 10 and 15 letters. Well, that's less than 16, right? And then now what about this one here? It's almost always the hardest one to satisfy. Well, what is T is 16. At least we're wanting to work with 16. We're checking to see if that's enough. Is 16 less than or equal to n plus m, regardless of what values are chosen that satisfy these 2 inequalities? Well, 16 is less than or equal to that because the smallest n and m can be individually is 10. They're going to have to be at least 10. So that would give us, at a minimum, 20 for the total, for n plus m. Well, 16 is less than or equal to 20. So that works just fine as well. Okay? So that shows that the opening routine will work if you use 16 cards. Now, would it work if you used 15 cards? Think about it. This inequality would still hold, this one would hold, and even this one would hold, right? Because we'd have 15 as smaller than or equal to 20. What about 14? Would t equal 14 work? Well, it might, but not necessarily, because if either one of you chooses one of these longer card names, we're going to run out of cards. You'll need 15 for Queen of Diamonds, let's say. Okay, so that's not going to work. So far, 15's fine. 16. What about 17? Could you actually use 17 cards? Well, the first 2 inequalities will work just fine, right? Because n and m cannot be any bigger than 15, and both of those are less than 17. So the only concern is over here. Is it true that 17 is less than or equal to 20? Well, it is. In fact, that kind of reveals what range of values you can use, right? So you can use anything in this range for t. The total packet size could be between 15, 16, 17, 18, 19, and 20. Any of those values would work for this routine. Well, what that allows you to do is, now this is going kind of beyond what we've done today, but what allows you to do is if you happen to know the bottom card of the deck, which is not too hard to know, look at these values, 15 to 20. Well, isn't that about a third-ish, plus or minus, a third of the entire packet? Okay, so what you could do is you could cut off about two-thirds of the packet, just estimate. It doesn't have to be exact. It just has to be in this range, okay? And, toss those aside. Remember, you know this card. And then this spelling routine could work just fine. You could sandwich their favorite card between your favorite card to find your favorite card in the deck, the three of hearts, supposedly. Okay, so maybe they choose two of diamonds. Okay, so you're going to sandwich theirs between yours. So you're going to spell out three of hearts. So THREEOFHEARTS. Okay, and then two of diamonds was theirs. Fine. TWOOFTIAMONDS. And now you're going to sandwich it between the three of hearts, which is your favorite card as the performer. THREEOFHEAHEA. I'm not sure if I did an A or not. RTS. Okay, so if I spelled that out correctly, there should be the three of hearts. Okay, I did. Okay, because I kind of stopped mid-counting. Okay, so anyway, that's pretty powerful. And this also explains one of my shorts where I use the phrase, your card is the. That's a fun one, actually. So look that up. It says, your card is the, and then something, okay? And so what I do is I spell out your card is the. How many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 cards. Okay, so correction. A little correction to what I said. So how that routine works is I cut off about a third of the deck. You can kind of watch it, about a third of the deck, just like we did. Okay, I show them the bottom card. That's what I did. I showed them the Queen of Spades. I say, remember, this is your card. Okay, and then I kind of use this as a lie detector. I say, okay, we're going to go ahead and just spell out your card is the, and then we'll spell the name of your card, and then we'll spell out your card is the, and then see if you were lying or not. Okay, well, notice that, as I mentioned, there's 13 letters here. So this is like N. So we're going to sandwich. So N is 13. Now M, the card that they happen to have seen, which we actually don't know what it is, but we do know it's going to be between these two values right there. Okay, so it's going to be between, the shortest will be 10 up to 15, okay? And then we'll sandwich that in between this phrase. So as far as counting cards, it's going to be, we'll say your card is the, so we'll spell that out, 13, and then we'll spell out whatever card name they give. So let's call it M, and M is up above, right? And then we'll sandwich that between the phrase, your card is the, which has 13 letters. And then this will bring theirs to the top so that when we spell out your card is the, and then we spell out what they claim their card is, technically they could state any card, and then we spell out your card is the next card is guaranteed to be the one that they actually saw at the bottom of the original packet of that third of the deck. Okay, and so when that's revealed, we'll know whether or not the card they stated was actually the card they saw. So we'll know whether or not they told a lie. Okay, so can you see how this would work? So why would about a third of the packet work? So if n is 13, m is 15, then we just go back to what we talked about here, right? Because as long as the packet, so the number of letters, like right here, the number of letters in any card name is between 10 and 15, okay? Now this time we have 13 for n. Well, it's in our range, okay? So for the very reasons that we gave here, these particular values are going to work when applying the sandwich principle. Okay, so this is guaranteed to bring to the top the original bottom card that the spectator saw. Okay, and then I want to point out, because I don't want to belabor this series, because technically what we've shown you today with the sandwich principle covers everything that I was hoping to cover in this third time's a charm. Okay, so let me just point out how I originally thought to kind of break up the different parts of this series, but in some ways it took a little turn that enabled us to explain all of it today, actually. All of the remaining kinds of routines you can do with this principle. So what I had done is I had separated even size packets, if you recall, from what I call any size packets. Okay? Well, really what we've been doing here with the sandwich principle, we were not necessarily confining ourselves to even size packets, and you don't need to. Okay? So just for completeness, what I thought I would do is just display this for the mathematically minded, and you'll just see that it generalizes what we did at the very beginning with even size packets. Okay, so let's just compare and contrast these really fast. So this is for those who want to look at the detailed write-ups I had created for this series, but in some ways we consolidated what was going to be kind of a second portion of this series. We included it in the second half of the video today, actually. Okay, so here is the write-up for even size packets that we've been going through. You have an even number of cards. You do that by Klondike shuffling n pairs to the table. And then you can go below n for the first and third coatings, but you have to go above n for the second coating by a certain amount that we talked about today. And a similar thing here, you can go above n for the first and third coatings, and then you can actually go below n for that, okay? Now, the only difference here is that when you have any size packet, so let's say it's odd, well, an odd number doesn't divide evenly into two equal portions. Well, to rewrite each of these in terms of this more general case, it gets just a little bit messy here, because technically this capital N divided by 2 could be a non-whole number, but it still gives you a range of values. You just go with all the whole numbers between this value, whatever it is, and the total number of cards being dealt. Okay, so it just gets a little messier to write this out in the case of a general packet size where it might be odd, okay? But if you were to kind of just study this, you realize that everything here is a direct generalization of what I have on the left, okay? But as explained in this video by way of the sandwich principle, you don't really need to understand this degree of detail right here. Okay, so anyway, I just wanted to explain that this brings our little series devoted to third time's a charm to an end, even though I may create more examples of this principle.